Hi, everybody. Welcome to another General Interest SharkNet webinar. My name is Armin Sobani, and I'm SharkNet HPC Technical Consultant based on Ontario Tech University. And this is my email. So if there is a question in your mind after this talk is over, you can contact me directly. Today's topic is about using C++ parallel algorithms in a distributed memory setup, or in other words, MPI, and see if it's even possible to do such a thing. In today's talk, first I will very quickly introduce C++ standard template library, or STL, and a recent welcome addition to it, C++ 11 parallel algorithms. Then I'll continue with partition global address space, or PGAS for short, parallel programming model and its advantages over shared and distributed memory models. Next, I will introduce Dash, which is a PGAS implementation in the form of a C++ template library. Last but not least, a live demo of building and running programs with Dash, and some benchmarks will be presented. You can find materials presented during the live session in the following repository on GitHub. So, standard template library, or STL for short, is a fundamental part of the C++ standard. And it's influenced many parts of the standard library. It consists of 4 major components. Containers are generic implementations of major data structures. Iterators act as a generic interfaces for accessing some or all elements of containers. Algorithms use iterators to manipulate containers. And finally, some generic functions and functors or function objects are there. So for a long time, there was an interest for inclusion of parallel version of STL algorithms into the library. You may ask why. Because the standard interface used in STL algorithms is familiar to most C++ programmers. In addition, there are numerous applications and libraries that have already used these algorithms, which can be easily ported to parallel version. Fortunately, parallel algorithms are now part of the C++ ISO standard known as C++ 11. And there are quite a few almost complete implementations available for both CPU and GPU. For example, Microsoft Visual Studio starting from version 15.5 support that. And also there is an Intel's open source parallel STL available on GitHub. All these 4 here are examples of CPU implementation, but there are also third-party C++ libraries for GPU implementation. For example, boost.compute, Trust by NVIDIA, and Bolt by AMD. These are covered in more details in 2 previous general interest webinars. But there was an interesting, frequently asked question during those webinars. Is it possible to use parallel algorithms in an MPI setup? The straight answer to this question is no. Why not? Because it requires a new type of containers that are distributed among MPI processes. And there is also need for a new types of iterators and algorithms that support both local and global iterations, a concept also known as affinity that I cover later today. But this is not the end of the story. There is an alternative solution which doesn't have all the bells and whistles of C++ 11 parallel algorithms, but has more or less the same interface. But before going in for that, we need a little bit of background. When it comes to program parallel machines, there are two most widely approaches for parallel programming: shared memory programming using threads, and distributed memory programming using message passing interface, or MPI for short. As you can see in this illustration, shared memory programming using threads, in shared memory programming using threads, all the CPU cores can access the same memory. Each core or process has access to its private data and also access to shared data, which is shared between all cores or processes. OpenMP, POSIX threads, C++ threads, Java threads are all the programming models or technologies that are based on this shared memory programming model. The good thing about this approach is it's easier to use and program, and communications are implicit, and there are direct read and write to the memory by each core. But there are some drawbacks. For example, these architectures are hard to build from the hardware point of view. So you can't make such a shared memory model computer in your home. They must be built in a factory, CPU factory. And there would be also race conditions, and one of the most important thing that is prevent this approach to get the best performance is the concept of false sharing. On the other hand, in distributed memory programming using MPI, the CPU cores or processes cannot access the same memory. Each core or process only have access to the private data, and there is no shared data. And they need to use messages to share the information between them. The good thing about this approach is that it's easier to build. You can build, a cluster, for example, using Raspberry Pi computers and network in your home. And it's very efficient and scalable. There is no false sharing, for example, here. But the problem is that it's hard to use and program. There is also data replication and redundancy, because you need to put some of your data on all processes or all nodes, for example. And there is explicit coordination of communication and paired send and receive. Then comes partition global address space, or PGAS, which offers best of both worlds. As you can see here in this illustration, in PGAS, each cores have access to the private data and also shared data, but this shared data is distributed among all the processes. So it can be used on large scale distributed memory as well as shared memory architectures. A PGAS program looks much like a regular threaded program, but sharing data is declared explicitly and data partitioning is made explicit, which both needed for performance. PGAS relies on several technologies depending on the implementation. One-sided communications in MPI, or remote direct memory access, or RMA for short, non-blocking synchronization, non-uniform memory access, or NUMA, cache-only memory architecture, or COMA, are among the few. But what about PGAS implementations? No matter what the implementation is, there are some common runtime middleware layers that exploit the remote direct memory access feature of networks. GasNet, ARMkey, GASP, OpenSHMEM, and MPI3 RMA are among a few. PGAS implementations are built on top of one or more of these middleware layers and are in the form of language extensions like Unified Parallel C or UPC, Query Fortran, Split C, or languages, for example, Sun's Fortress, Cray's Chapel, IBM's X10, or libraries like UPC++, Query C++, Shimem, and Dash, which is the subject of today's talk. So let's see how PGAS works in Unified Parallel C or UPC terminology. Let's call the members of our program threads. And let's assume we used single program, multiple data paradigm. And let's assume we have a new keyword shared that puts variables in the shared global address space. So by having shared int hours and int mine, we have one copy of ours accessible by every thread, but it resides on thread 0. These dashed lines represent that all these threads have access to ours. But there are also n copies of mine, one per thread. Each thread can only access its own copy. But let's see what happens with shared arrays. A shared array example in UPC is like this. And if we have a 4-element array like this called ours, then each element of this array is accessible by each thread, but each of them are located in one of these threads. Here, we come to affinity concept. That means in which partition a data item lives. So for example, ours in previous slide lives in partition 0 by convention. But ours I, or each element of the array, lives in partition I. For example, ours 1 lives in partition 1. There is also a concept of global view versus local view in PGAS. There are two ways to organize access to shared data. One is global view, which if we want to express it in UPC terms and show it like this shared int x with 100 elements, here x is declared in terms of global size and also accessed in terms of global indices. And the process, which is a term in MPI, or the synonyms for that is image in Fortran, Query Fortran, is not specified explicitly here. But we also have local views, and this is, for example, a Query Fortran version of it. Here, A and B are declared in terms of their local size and also accessed in terms of local indices. And process or image is specified explicitly using the coindex. So in summary, PGAS is a concept realized in, for example, UPC and other language extensions or programming languages. So for example, in UPC, which is an extension to C, implementing the PGAS model, is like an extension to C. But it's built on top of a middleware layer like GasNet, but it can be different the middle layer, like for example, even MPI 3. And UPC, for example, is available as a GCC version, Berkeley UPC from some vendors. But for most of them, there are some drawbacks. For example, they are often not part of the standard software stack of HPC systems. For example, we don't have most of them in, Compute Canada stack. They are tricky to install and tune for individual users. And there is also no collective operations or algorithms. For example, reduce in the STL doesn't exist in this kind of implementations. That brings us to DASH. DASH is an effort by 3 German universities and an HPC center to develop a PGAS implementation in the form of C++ template library. This is the official website for the project, and the repository is on GitHub. Its main focus is on data structures, or in STL terms, containers. For example, here, array A can be stored in memory of several nodes. AI transparently can refer to local memory or remote memory via operator overloading, which is a feature in C++. So the good thing is that there is not a new language to learn, and Dash can be integrated with existing MPI applications, and it relies on MPI 3 API, which supports RMA. It also supports for hierarchical locality, like team hierarchies and locality iterators. So let's explore Dash in more details. So Dash is a complete BGAS programming system without a custom compiler. And it offers distributed data structures or containers and parallel algorithms. And these algorithms have conformity with STL iterator interface. Another good thing about this library is that it has support for HTF5 file format out of the box, which is common in scientific programming. Here is a hierarchy of the Dash application. This, a developed Dash application talks to Dash C++ template library, which is on top of a Dash runtime, which is another library in C and is called Dart. Dart is it developed in plain C 99 interface. It uses SPMD, or single program multiple data execution model, and it defines units and teams. It supports one-sided RDMA operations, and there are several implementations of Dart for different middleware layers. For example, GasNet, GasB, CUDA, and MPI3 RDMA, which is the default workhorse. So what are the units and teams in Dart terminology? Units are individual participants in a Dash Dart program. So unit is synonym to processes in MPI, threads in UPC terminology, and image in query Fortran. Execution model follows the classical SPMD paradigm, and each unit has global ID that remains unchanged during the execution. Teams, on the other hand, are ordered subset of units identified by an integer ID, and the Dart team all represents all units in a program. Units that are members of a team have a local ID with respect to that team. So here, let's see how PGAS in Dash works. So data affinity, for data affinity, the unified access to local and remote data in global memory space is like this. So for example, if we have a dash array with 40 elements here, if we use unit 2 to access, for example, element 27, we can use global memory space or global indices. But when we are on unit 2, using this semantics refers to, uses the local access. But on the same unit, if you use ARR35, which global indexing, it refers to element in unit 3. So you can use both local access and remote access using the global indexing. But there is also explicit views on local memory space. So here, if you are on the unit 2, you can use .local to explicitly refer to local element using the local indices. So you can use 7 to refer to that unit, but you can't have access to other units using the local one. So here is a hello world in dash example. So you need to include the main header file, and the namespace for dash library is dash. Like any MPI program, first you need to initialize the programming environment, and then you can determine total number of units and our own unit ID. This is the number of units, and the unit ID is like this. And then we can print the hello world from each unit, and the sample output will be something like this on, for example, Graham login node. So let's see how global view and local view are referenced in Dash. Dash supports both global view and local view semantics in a way compatible with STL. When you want to refer to a range in global view, you can use the ordinary begin and end like the standard, STL containers. And you can use the size for the global size of your array. And then you can use the subscript operator like ordinary array in STL to refer to those elements globally. But if you want to switch to local view, you can use the .local before each of these, or there is a shorthand version for begin, end, and size, which you can drop the .local and just use lbegin, lend, or lsize. So if we have a dash array, for example, with 14 elements distributed over 4 units, the default distribution, which I cover later, is blocked. And this formula is used by Dash to calculate the block size. So here the block size will be 4, and the last unit has only filled 2 of them, and 2 are empty, for example, for 14 elements. So here, if you use begin, then begin in all units refer to this position or element 0. And end refers to this position in all units. But if you use lbegin, depending on which unit you are, it can refer to this one or this one or this one or this one. And end is also like this, different based on the units. So you can use distributed data structures in Dash like this. Here, for example, you can use the global addressing to fill an array, a dash array, which is distributed among the units. So for doing that, you need to first switch to only one unit, and then use the global addressing to fill that. When you use this approach, it's not going to be parallel. You just use one core to do the whole filling. And then you can use the same unit to printing. But the good thing is that all the values that you put are distributed among all the units. But all the work is done by only one of the units, and the other ones are idle. But using this local addressing, using the same for, but this time using L size for the local size, and then using the local addressing, which you can replace this one to L size, but local is like this. You should always use the local, but you can use auto to assign it to a pointer or local pointer. And if you fill that with, for example, the unit ID, you can get a result like this. The good thing is that when you use the local referencing, it's automatically paralleled among all the units. There are also, because Dash containers use the STL convention, you can use all STL algorithms on, for example, Dash array. But the thing is that for some of the algorithms like fill or generate, the only thing that you need to use is to use local addressing, and it's automatically the whole thing, even using the standard fill algorithm, will be parallelized through all the units. And that's the beauty of PGAS implementation in this sense. But the thing is that for some of other algorithms, for example, sort, you can't do simply like that because sort needs to work between the units. And the standard sort by STL, provided by STL, doesn't support that. So if you want to sort the whole array, Dash array, you have to do it using only one unit. For example, we used unit 0 here to do the sort. So all the units, now all the standard template library algorithms can be used on Dash containers, but there are some things that you should consider. And when you do that, you need always at the end do Dash finalize. And even on previous examples, I forgot to mention that you need to sync all the units after doing such a loop like this. So what distributed data structures are available in Dash? There is a one-dimensional array that we already covered, but there are also n-dimensional arrays with n arrays, which can act as a matrix also. There is a shared one, which is a shared scalar, and by default it's fixed on unit 0. So those that are shared between all units are going to be put in the unit 0. There are also list and map, and directory is under development. Maybe will be available in next version of Dash. Dash also supports data distribution patterns. So for example, by default, when you define an array, the default distribution is blocked. But there is a second overloaded argument that you can use to mention the type of the data distribution pattern. So the default one is blocked, which puts using the formula that I showed you in the previous slide, calculates the size of the blocks and distribute the elements among the units like this. So 5 elements, for example, in this example goes to unit 0 and the other 5 to unit 1 and etc. In cyclic pattern, each element is stored in the next unit, and then it's the cycle through our units again. And there is also a block cyclic pattern that you can mention the size of the block. And for example, if you want to store three-dimensional points X, Y, Z, maybe you decide to use this block cyclic pattern to put X, Y, Z of each point in different nodes, for example. The n-dimensional array, which is n array, also there is a synonym for that, which is dash matrix. It represents n-dimensional array in dash. The first argument for the template is the type of data, and the second one is the template is the size of the n-dimensional array. Then you can refer to each element using Fortran style access or C chain subscripts access. And you can also access it using the local iterator. Patterns can be also applied to n-dimensional arrays, and blocked cyclic and blocked cyclic multiple dimensions are all supported like this. But what kind of dash algorithms are provided? The good thing about using dash algorithms is that when they are provided, there is no need to use the lbegin, for example. So there is a dash fill algorithm that you can use instead of a standard or std fill. And when you use that, you just need to use begin and end rather than lbegin and lend. The good thing about these algorithms is that for some algorithms like sort that I mentioned, it's not possible to use just local indexing to do the whole thing in parallel. And they must be implemented exclusively by dash or by the programmer if they are not provided by dash. So these are the, some of the good algorithms that are implemented in dash currently. The good news is that the two workhorses of functional programming paradigm, map and reduce, are already there. Unfortunately, filter or remove if in C++ or STL terminology is not there yet. So for example, if you use the min element dash algorithm, which finds the, the minimum element in an array, the good thing about that is that it's the dash version algorithm still works when using different path distribution patterns like cyclic, and it still works when using a range other than begin and end, and it's all paralleled among the units. Here is a chart of performance of dash min element, for example. The gray line here is the ideal scaling. And you can see as the number of elements increases, it gets better scaling. So how we can use dash on Graham? The home page of dash is here in this link, and the Git repository is here. For compiling it, you need C++ 14, and also you need an MPI implementation that supports API 3 or higher. To do the whole building, you can use the following commands on Graham, for example. You can go to the scratch and get the latest release and then cd to dash. And these are the compilers that and the tool chain that I figured out that work good on Graham when you make the dash, and then you can use these commands to build and install dash in your home directory. After doing that, if you want to compile a dash sample, for example, hello CPP, you use the dash provided script, which is which adds some linking and header libraries to default MPI compiler. So you need to use dash MPI CXX command to compile your C or C++ code. And for running your program, you need to use MPI run or srun in the sbatch script. For the live demo, I've developed a repository that gives you a head start to experiment and develop with Dash library, especially on Compute Canada cluster. It's based on CMake build system. The good thing about it is if it cannot find Dash library, it tries to download and build it automatically, so you don't have to do it yourself. The repository is in the following link at GitHub. So let me now switch to repository here. So when you click on that link and check the whole first page, for building from source, you need the CMake. You need a CMake version 3.9 or higher. You need also a C compiler supporting C99, which most of the C compilers now support that. But you need a C++ compiler supporting the C++ 14 standard. It requires the only library that it relies on, that is, as I said, is OpenMPI. You need an OpenMPI which supports API 3 or higher. If you want to check that if it's supported on the your system, the system that you want to compile, you can use this. For example, if I run this command on Graham login node, I can see that the default MPI API is 3.1, which is higher than 3. So you're good to use. There are also optional third-party libraries, which is Dash and Google Benchmark for some of the benchmarks that I included in the repository. The good thing is that, as I said, you don't need to have them installed. The CMake script check if they are installed, it uses the installed version, but if they not, it tries to download and compile them and build them. So you don't have to be worried about them. So in order to build that on Compute Canada, for example, clusters, Graham, Cedar, Beluga, you can use these following commands. So let me do that one by one here. The main one that I need first is this one. So I first switch to Scratch folder and then clone the repository from GitHub. And then cd to the folder here. The next thing is that loading the modules that I figured out works best for this build. I switched to GCC 7.3 and also corresponding OpenMPI. And then you can do make a build directory. Here you can use the CMake dot to configure the whole thing. So here is already discovered the C compiler, which is C and C++ compiler, which is new 7.3. Then it tries to find MPI, which is version 3.1. It couldn't find -MPI, which is not provided by module system, and I haven't installed it on my home folder. So it tries to clone dash and dart from the GitHub repository. It takes a while to download, depending on the connection speed. And then it tries to configure it. You can do the same thing on other Compute Canada clusters, for example, Beluga or Cedar. Okay. So it tries now to configure both Dash and also Google benchmark. And when it's done, it says that configuring done, generating done. After it's finished, you can use make help to see the available options. For example, you can build only the programs that or examples that you like. But if you want to build the whole thing, you can use make. And let me first check how many. So because there are only 3 cores used on login node, I can make using 10 concurrent cores to speed up the whole build. After the build is finished, here you can find the compiled version of examples in the example folder. So if I go to example, here I included 4 example programs. Let me show you the source one by one in, on Visual Studio Code here. The first one is the Hello World sample. I used also the color coding to differentiate between different units. So the whole thing is really simple, and I already showed you. And at the end, we call dash finalize. So to run all these programs, you need to use MPI run and specify the number of processes that you need. For example, 4 here, and then the name of the program. For example, Hello MPI. So each unit prints in different color and prints depending on the order may be different on each run. But the thing is that if you change the number of processes, for example, to 8, it becomes like this with different color codes. The next example is global one that uses the unit 0 to fill the whole array with incrementing numbers. So if I use the same for global MPI, you can see the output by default, the array size is 100. But the first argument to the program can change that. So if I want to have it for 512 array size of that, I just use this and it increases. And if I want to increase the number of cores or processes, I can use this. So all these elements are in unit 0 and then unit 1 and etc. And the next sample is the local version, which uses the L size and puts the unit ID to that, and it happens in parallel. So if I do local like this, So all these zeros are in unit 0 and ones are in unit 1 and etc. You can increase or decrease the number of cores or size of the array. But the next interesting thing is the generate. This here, I use the standard generate algorithm to put random numbers between uniformly random integers uniformly distributed between 0 and 100. The default size for that is 512, but you can increase that as a first argument. The thing is that if you can change this one to dash version of generate, and it produces exactly same output. The only difference is that if you use the dash generate algorithm, you need to use begin rather than lbegin and len. So let's see the output of this using let's use the 10 processes. So these are the random number generated. This is the number of units 10, and these are the random numbers. These are all in unit 0 and unit 1 and etc. In the next sample or example, in addition to generating random numbers, I use the dash sort to sort all these values. So let me do that here with sort. Now you can see that all these generated randomly generated integers are now sorted, and each of them are in different units, as you can see here. But the whole sort happens in parallel. So how you can tell that? For the next example, I included two benchmarks, one for generate random and another one for the sort. This sample uses the Google benchmark to do the whole benchmarking. When you do that using when you want to do an benchmark using Google benchmark with MPI protocol, you have to develop some boilerplates that you can find it here. So if you want to replace your thing, the place that you need to put your code is here. The unit of code we want to benchmark, I commented like this, must be inserted here. For generate, we put it here, and then we call barrier, and it's gonna measure the whole thing. For the sort, please note that we need to first generate and just put the sort part in here. So we can just measure the sorting. So if I try to do that here, I just change to all these benchmarks are in perf folder. There are two. So I can use MPI run again. First, I use for process to run the perf generate. So it tries to increase the number of elements in the array from this to this. And these are the time in milliseconds. So I expect that it tries to, this time it tries to generate random floating points between 0 and 1, if you check the source code. So I expect that if I increase the number of processes to 8, the all timings, if there is a good scaling, become half. So let's see. So it's almost like that. And because I'm not on a dedicated node, I'm just on the login node. But you know, the load average is about 2. So because I use 8 and the number of cores on login nodes are 16, I'm good. So you can think, you can see that it's almost, you know, half. So there's a good scaling, but I can increase that to more. The thing is that for the generate, it can scale really well, even if you go to, you know, bigger numbers, because each process can do on their data independently. But for another algorithm like sort is not like that. So let's check it. So this one is, let's run sort MPI. So for the same sizes, it takes more than generating, for example, 21 millisecond rather than 1.81. And if I double the number of cores to 8 or processes or units, it's good. You know, that at least for these numbers is that the scaling is good. But if you go to higher numbers, it may not as good as, you know, the generate random. The last thing that I am going to show you here is that usually when you switch to the, you know, PGAS and those things, you want to deal with the really large arrays and have a really high number of cores or processes in an MPI to do that. So let's try this. For doing that, I need to submit this job because I'm going to use a higher number of cores and a very large array. You can find a sample Apache script here at the end of this README page on the repository. I just copy and paste it here. Let me vi and run sort MPI sh. So the only thing that you need to change here is the account to yours. I change this one to cc debug. And increase the number of processes to 120. 120 is beyond any node. So the typical nodes on the Graham have 32, you know, cores, not cores, 32 processes. So 120 is it requires several nodes, and I intend to run it on a 10 an array with 10 billion floating points. So let me save this one for here and edit my sort example here. I change this line, these two lines. I comment these two and just use an array with this size. Let me see. 1, 2, 3. Yes, let me make it like this. So it's 10 billion now. After this change, I need to make it again. So it compiles the source benchmark. The thing is that when I have 10 billion floating point, the memory that I require for that must be about 40 gigabytes. So I need to, if I check this memory per CPU, because I have 120, and each with 1 gigabyte, I have 120 gigabytes, and it must be enough. But I don't know why. Maybe it's something that's the MPI implementation that is on Graham with this version of MPI that I use for compiling. I had to change this one to 3 to prevent out of memory. But I did the same thing on Cedar, and using 1 gig for per CPU, it worked. I don't know, still don't know why, but it's the way it works on Graham. So let's have it like this, and then use a batch to submit our job. So it's running, and if I check here, so it's still working on the benchmark. Not finished yet. So these are the nodes that are working on this, and we used 120 cores to sort 10 billion floating point variables. So already finished. Now if I cat slurm, you can see that it's finished in 16,000 milliseconds. So if you want to check the scaling here, we can do, I don't know if I can, let's try it once more. I can reduce this number to just 12. But if I put 12, I need more memory there. So maybe 60. But because we are already past the time, let's escape this escape and see what are your questions. But you get the whole idea. Using this approach, you can have more cores working on a problem and with less memory on each course rather than using, for example, the threaded version.